the right one is. So go ahead.
All right. Nowadays, everyone wants to integrate AI and ML solution into their work, but the problem is how to properly develop and deploy and maintain these solutions. My name is Mostafa, and I'm here today to present our paper on bridging the gap between the machine learning development and service-oriented computing. Alexander and I are with the University of Groningen, and Viktoriya is with the University of Amsterdam. We have other partners in this project, which is evolutionary changes in data analysis called SIDA, a bigger project that this paper is part of. And these partners are Vitens, the largest water distribution company in the Netherlands, TNO, research organization, and researchable data company. All right, with these slides, I want to give an overview of the problem. On the left side, we have service-oriented computing, which is an island that is more mature with more developed buildings. The jobs there are has some kind of predefined logic or has a clear scope. And on the right side, we have machine learning development, which is evolving, has probably it's more advanced, shiny buildings, but it's less developed. And due to its probabilistic nature, it has more iterative tests. And one main also difference is that in a service-oriented computing community, the development is for production. So not everyone knows that the service will eventually show up in production. But in machine learning development, the development is for exploring the possibilities, exploring the data, the models, and you cannot expect like the development is ready for for production, and it needs more stages. Our vision is to build a bridge based on these 6 components: automatic module composition, automated module selection, version control, monitoring, CI/CD, and what-if scenario, which I will explain in the next, let's say, 18 minutes. And it's using adaptive runtime controller as an interface to run these applications on the infrastructure. Okay, now let's introduce how ML and AI workflow works. We have beneficiaries and AI teams working together to come up with business requirements. Then they will continue working on preparing the data. After that, the AI team can work on developing some solutions. Here we have our first feedback, or going back probably due to insufficient data or low quality data. We have to go back to data preparation. On the next stage, we have application deployment, where the DevOps teams comes to play, and they incorporate with AI and ML teams to make applications ready for deployment. And here we will have a number of iterations going back from application deployment to ML development, and so on, back and forth, because as I said, the development is for exploration, and there will be lots of probably dead codes in Jupyter notebooks, and so on. So there will be a hard job doing this. And then in the next stage, we have monitoring. We need continuous monitoring for our applications to make sure that they perform as intended. And when we are monitoring our application, we may need to go back to AI or ML solution development, or we may go one step back to data preparation. And also, there may be some change to business requirement, which may need to change everything in the past. All right. So now I will introduce a bit about what is a data processing pipeline, how we see it. we have some individual components, probably general like pre-processing, we have a number of them, a model, post-processing. And using these components, we can create pipelines. For example, as an instance of this pipeline, we have two pre-processing, a stage, model, and a post-processing. And due to the changes that I described in the previous slide, we may need to change hyperparameters of the model, or we may need to add more components, swap a component with another, so we need to have some change in the pipelines. And to capture this change and adapt to these changes, we want to promote modularity in ML development, and we distinguish two levels of modularity. First one is algorithmic modularity, which is the modularity on level of code, which, like for example, thanks to this framework such as scikit-learn, data scientist leverages this level of modularity to a good extent. And the other level of modularity, which we want to focus on this work, is architectural modularity, which is like instead of having all the components in the same code in one place, packaging them separately, so we can best use the benefits of modularity, like changing the components on the fly, probably on the protection. Adapting service-oriented computing, everything as a service, we introduce everything as a module, which is there to capture the differences between conventional web services and machine learning web services, which are, like for example, we have hyperparameters there in training, inference. We have different modes of running a single module. And for defining a module, we use two different components, like a module definition, which serves like an API for, or like VSDL, web service definition language for web services, to define what this black box module looks like, so to give us some information. And the module implementation is actually putting this definition to the practice. So it's like the actual code probably, or Docker container, or whatever, for implementing this definition. We can have atomic module, and we can have a composite module, like we have in the service area, atomic service and atomic, and composite services. So on the left side we have a definition registry. So we have three different definitions: numeric classifier, scalar, and a classifier. And we may have also an implementation registry where we have implementations, module implementations, support vector machine, k-nearest neighbor, min-max scalar, and a standard series. And we want to create new composite modules, customer segmentation. So first we have to pick a definition, so we know that for customer segmentation, we could benefit from a numeric classifier. And as the implementation, we will compose a new implementation. And for that, we can create a pipeline by picking, for example, a scalar and then a classifier. Now we have half of the modules because we have the definitions, we know how they are connected to each other, where the data comes from, and how the data flow in this composite implementation. And now it's the time to pick the right module implementation for each module. So like we have two different implementations of a scalar, min-max scalar, or a standard scalar, that we can fit in this place. And we have support vector machine and a k-nearest neighbor that can fit in this place. And we need a combination of these two that works for us. So then we can fill these gaps, and now we have our composite machine. So this was an example of how to do it by hand, but we can automate this process and have the automatic module composition. Okay. The next thing that I want to address is version control. So like in a traditional, let's say, software development, we know that each next version is a better version. But in machine learning development, the next version should be put into probably some testing, some even like a production practice to see how it performs. It may be better, or it may work with the next version. But what we want to see in production is to see only the best ones. We need to take care of versioning for that. And with this solution of seeing everything as a module, we can see, like, for example, training data as a module, training configuration as another module, ML code is another module. So everything is a module, so we can have a standard way of versioning different components of machine learning. And the next thing is monitoring. And here we also want monitoring as a module. So let's say we have a very basic pipeline with 3 components, pre-processing, model post-processing, and we want to introduce a new monitoring module for anomaly detection in the very beginning, data drift detection, scalability monitoring, model evaluator. So like, you can add different monitoring modules on your request. So like, as I said, like, everything is a module. Monitoring modules are modules. So we can have another monitoring module that gets the data from other monitoring modules and probably generate signals for retraining this pipeline. Right. The next thing is lifecycle management. With this lifecycle management, we have automated module composition. So the user will ask, for example, to compose a module. Then this smart component will generate this module and send it to what if scenario. I guess what if scenario, it's probably not the first time that appears, but I didn't explain it. It's for testing different situations. Like, for example, what if there was this configuration on this pipeline? What if we train this model, this module with this data, and so on. So like we create different scenarios and put each scenario into different isolated environment to test our module, or composite module, or let's say our pipeline, and get some insight using continuous monitoring and putting the data into a monitoring database. And now we have probably some good experiment tracking, and this adaptive module selection can pick, for example, the best performing training configuration, or best performing model to put it in the production. And this cycle will go on and on to always make sure that you have the best performing model in production. We put this vision into practice, and for that we built a CEDA platform where the user submits the module codes to a module code base on GitLab, and then our continuous integration for the GitLab CI that we develop will containerize the module and put it in a Docker registry. Also, it will create and push the modules to a deployment repository. These are the descriptions of the modules that will go to the deployment repository. To be more specific, there are Kubernetes custom resources. And then after the user pushed their module codes and they are already in the repositories, the user can interact with the user interface to create and manipulate pipelines. And here you may have tons of modules, and you may not know where to start and how to create your pipeline. And for that, we have automatic module composition, which we implemented using GPT-3. So you can ask the GPT, like, I want this pipeline with this configuration, generate me a pipeline. It will generate, but as we know, it may not be the best one, or it may not be even correct. So you can have discussion with this AI, like change this one for me, or do something, and then you can iteratively make your pipeline works better, like the way you want. And to this point, now the user work is done, and the rest will be taken care of by the platform itself. Argo CD is the continuous deployment solution that takes the resources, and we have our own controllers on top of Kubernetes to deploy these pipelines. And for the pipelines, you only need to select the modules and say, like, I want to connect this module 1 to module 2. And then also the communication channels and everything will be handled by this adaptive runtime controller. And as I said, like, we want to eat our own food, and monitoring is also a module. So we have a number of monitoring modules that gets the data from data pipelines and push it to monitoring database that we use Prometheus for implementation. And then we have two smart components: adaptive module selection and, as I said, robotic component to check the monitoring database and generate new configurations and put into this deployment process. And then the rest will be taken care of by Argo CD and Kubernetes, and then this cycle will go. Just to show you some user interface, you have modules here. You can search them by what filters count them by some by names, and also select them, drag and drop to the canvas, connect them together the way you want. Probably if you have some issue of how to create it, you have this suggest button where you can communicate with the AI, with GPT-3. You can, for example, specify I want this input, this output, generate me a pipeline, or you can go completely with text. And you can also select a component and add a monitoring module to this component to get some insight. And this is the first real use case that we implement on our platform, which is from our client Vitens, which is the largest water company in the Netherlands. And this is one of these smart areas called Oosterbeek, which has around 6,000 nodes with only 300 sensors. And the problem here is to predict water pressure at every location. And we can run it as a streaming application to see pressures at some random time T1, T2. And the result proven that this is one of the best, or if not the best, model for predictions. All right, to come to a conclusion or a takeaway for this presentation, I want to emphasize that the gap exists, and the engineering aspects of data science is overlooked, and there are some possibilities and chances for us, the services community, to work on this area. For example, module compositions, life cycle management, training, and usage phase. There are two different phases of a pipeline with different requirements. Versioning, continuous monitoring, and also experiment tracking, because for now, experiment tracking has a very basic functionality to this lack of also version control, so you cannot probably, you don't have a good tool for model lineage. You will need these kind of tools, and also what if scenarios for automatically generate scenarios, finding corner cases, and so on, so to make your application work. At the end, if you want to do data science, but you don't want to engage yourself with engineering parts, we are here for you, and you can contact us. Thank you.
Okay, thank you, Mostafa, for presenting your work. Again, a few seconds for a very urgent question. Are Otherwise, we continue with the final talk for today. We move to the University of Hamburg. Benjamin Bollmer is a member of the group of Nova Twitter there, and he will tell us something about the usage of the client cache for content encoding. So the stage is yours.